Look up at the night sky, and what do you see? A peaceful, familiar expanse of stars and planets. Right. But what if I told you our solar system, the very space we call our cosmic neighborhood, is hiding secrets that defy explanation? Mysteries lurking in plain sight, challenging everything we think we know. Imagine the solar system as a grand detective story with 25 unsolved cases, each one more baffling than the last. Unexplained phenomena that scientists are still scrambling to decode, from bizarre objects behaving in ways physics can't explain to strange signals with no clear origin. Take Jupiter's Great Red Spot, for example. This massive storm has been raging for at least 400 years, possibly much longer, yet we still don't fully understand what fuels it or why it hasn't dissipated. Or what about the tiny moon Enceladus, spewing towering geysers of water into space from a hidden ocean beneath its icy shell? How does a world so small hold such vast liquid secrets? And then there's the asteroid Bennu, a space rock that seems to be ejecting material into the void for no apparent reason, as if it's actively resisting our attempts to study it. These aren't just scientific curiosities, they're cosmic puzzles begging to be solved. That's exactly what we're diving into today. 25 of the most jaw-dropping, head-scratching mysteries right here in our solar system. Phenomena that make even seasoned astronomers pause and wonder. Some might be clues to the origins of life itself, while others could rewrite the laws of physics as we know them. So buckle up, because we're about to embark on a journey through the strangest corners of our celestial backyard, where every discovery raises new questions, and nothing is quite as it seems. Saturn's North Pole holds one of the most mesmerizing mysteries in our solar system, a colossal hexagon so precise it looks like it was carved by some cosmic architect. This swirling geometric storm stretches 20,000 miles across, large enough to swallow 4 Earths side by side. Unlike any other weather pattern we've observed, this 6-sided behemoth has remained shockingly stable since we first spotted it decades ago. Normally, atmospheric turbulence tears apart orderly shapes, yet Saturn's hexagon has defied chaos for over 40 years, maybe even centuries. The sheer precision of its angles baffles scientists. Imagine tossing a pebble into a pond and watching the ripples form perfect triangles or squares instead of circles. That's how unnatural this phenomenon seems. Even more perplexing, the hexagon isn't just a surface feature. It plunges hundreds of miles deep into Saturn's atmosphere, like a gargantuan rotating tower of clouds locked into place. Current atmospheric models can't fully explain how such a structure persists without breaking apart. Some theories suggest standing waves, where energy ricochets at just the right frequencies to reinforce the shape. Others propose it's a mega hurricane, a storm so vast it's shaped by forces we don't yet understand. The Voyager spacecraft first caught glimpses of the hexagon in the early 1980s, but it wasn't until Cassini arrived in 2004 that we saw it in breathtaking detail. Infrared images revealed the hexagon's walls towering over the surrounding atmosphere, with winds screaming at over 300 miles per hour. Yet at its center lies an eerie calm, a massive eye reminiscent of earthly hurricanes but scaled up to planetary proportions. What's fueling this atmospheric enigma? Could it be tied to Saturn's rotation or hidden magnetic fields? Or is there something deeper, some fundamental physics we're missing? Every answer only leads to more questions, proving that even in our own solar system, nature still holds cards we haven't even glimpsed. While Saturn's hexagon is a marvel of geometry, Venus offers a mystery of motion, one that defies the very laws governing planetary behavior. Picture a world where the air moves faster than the ground beneath it, not just a little faster, but a staggering 60 times faster. That's the enigma of Venus superrotation, where hurricane-force winds tear through the planet's upper atmosphere at over 200 miles per hour, completing a lap around Venus in just 4 Earth days. while the planet itself takes a sluggish 243 days to spin once. This atmospheric rebellion has puzzled scientists since the 1960s, when early probes first clocked the planet's breakneck winds. Normally, a planet's rotation drags its atmosphere along with it. Think of Earth's gentle trade winds or Jupiter's banded storms, all moving in sync with their planet's spin. But Venus flips this logic on its head. It's like watching a carousel where the horses race ahead while the platform barely creeps forward. What's fueling this bizarre phenomenon? One leading theory points to thermal tides, sunlight heating Venus' thick carbon dioxide atmosphere, creating pressure waves that push the air forward like an invisible hand. Others suggest momentum from the planet's surface might be transferring upward through mysterious waves or turbulence, though Venus' lack of a magnetic field complicates the math. Then there's the sheer violence of the atmosphere itself, with sulfuric acid clouds circling the planet in a perpetual corrosive cyclone. Studying these winds isn't just a scientific curiosity, it's a survival challenge. Venus' surface is hot enough to melt lead, with pressures 92 times Earth's, making long-term probe missions nearly impossible. Even orbiters struggle as the dense atmosphere absorbs radar signals needed to map wind speeds. Yet understanding superrotation could unlock secrets about climate extremes, even shedding light on exoplanets with similar runaway atmospheres. Every failed explanation only deepens the mystery, proving Venus isn't just Earth's twin, it's a cautionary tale of how a planet can spiral into chaos. The morning of June 30th, 1908 began like any other in the remote Siberian wilderness until the sky split open with the force of 1,000 suns. A fireball brighter than the sun streaked across the heavens before detonating 6 miles above the Podkamennaya Tunguska River, unleashing a shockwave that flattened 80 million trees across 800 square miles. Witnesses described a pillar of blue light followed by a crash so loud it shattered windows hundreds of miles away. Yet when scientists finally reached the epicenter 19 years later, they found something even more baffling than the devastation: no crater. This gaping absence fuels one of the most enduring cosmic whodunits. Was it an asteroid or a comet that vaporized itself mid-air? Asteroid advocates point to tree rings showing elevated nickel and iridium, metals common in rocky space debris. But comet theorists counter with noctilucent clouds observed worldwide after the blast ice crystals flung into the upper atmosphere, suggesting a frozen intruder. Modern simulations reveal the culprit likely disintegrated explosively due to atmospheric pressure, like a soda can crushed in a vise. The blast released energy comparable to 10 to 15 megatons of TNT, some 600 times more powerful than Hiroshima, yet left no smoking gun. Even wilder theories persist, like Nikola Tesla's secret death ray experiment gone awry. Though dismissed by mainstream science, the timing is suspicious. Tesla had just published wireless power transmission plans months earlier, boasting devices that could split the Earth like an apple. Coincidence or cover-up, the truth remains buried in Siberian permafrost, where microscopic diamonds possibly forged in the cosmic impact still glint among the fallen trees. Every new expedition brings fresh clues, but the Tunguska event keeps its ultimate secret locked tight, reminding us that sometimes the universe delivers its messages in whispers rather than craters. Mars hides its secrets well, but 2 phenomena have scientists locked in fierce debate, clues that could rewrite our understanding of the red planet's potential for life. First, methane spikes that vanish as mysteriously as they appear. The Curiosity rover has sniffed out this gas multiple times since its landing in 2012, detecting bursts where concentrations briefly soar to 10 times background levels before dissipating. On Earth, 95% of methane comes from living organisms. Could the same be true on Mars, or is it the result of ancient geological processes like serpentinization, where water reacts with olivine-rich rocks to produce the gas? The pattern defies easy explanation. Some readings suggest seasonal variations peaking in northern summer, while others appear randomly like cosmic hiccups. Even stranger, Europe's Trace Gas Orbiter, designed specifically to study Martian methane, has barely detected any from orbit. This contradiction fuels speculation that something, perhaps ultraviolet radiation or surface chemistry, is destroying the gas before it reaches higher altitudes. Then there's the haunting case of recurring slope-linear dark, finger-like streaks that creep down Martian cliffs during warmer months and fade when temperatures drop. These features, first spotted in 2011, seemed like smoking guns for liquid water. Spectral data initially pointed to hydrated salts, which could lower water's freezing point enough to keep it flowing briefly on the surface. But follow-up studies revealed a twist. Orbital instruments couldn't confirm liquid water's presence. Some researchers argue these streaks might be dry sand flows instead, triggered by seasonal changes in temperature. The controversy highlights how Mars taunts us with Earth-like phenomena that may operate by entirely alien rules. The stakes couldn't be higher. If the methane comes from microbes, even extinct ones, it would suggest life took root in two places within our solar system. And if water truly flows today, however briefly, it would reshape our search for habitats beyond Earth. Yet every answer dances just out of reach, buried in the red dust of a world that refuses to give up its secrets easily. Jupiter already boasts the solar system's most famous storm, the Great Red Spot, but lurking in its shadow is an atmospheric oddity just as puzzling. Meet the Great Cold Spot, a dark vortex stretching 7,000 miles wide and twice as tall as Earth's atmosphere, where temperatures plummet hundreds of degrees below surrounding clouds. Discovered in 2017, this icy behemoth isn't some fleeting weather pattern. It's persisted for at least 15 years, possibly centuries. What makes this spot so extraordinary isn't just its size or chill, but its origin. Unlike the red spot, which churns deep within Jupiter's atmosphere, the cold spot appears anchored to the planet's polar auroras. Those dazzling light shows fueled by charged particles slamming into Jupiter's magnetic field. Scientists suspect these auroras might be dumping energy into the upper atmosphere like a cosmic air conditioner, creating a persistent cold zone. Imagine leaving your freezer door open and watching an entire weather system form around the blast of cold air. That's the scale of disturbance we're talking about on Jupiter. The contrast between these two spots couldn't be sharper. The red spot is a hyperactive storm, spinning like a furious top for centuries, while the cold spot feels more like a scar, a quiet, stable imprint of something far more subtle. Infrared telescopes reveal the cold spot structure isn't even a traditional storm, but a vast region of depleted particles, as if the auroras above are sucking warmth out of the atmosphere below. Yet mysteries abound. How does a feature so massive remain stable when Jupiter's polar winds should shred it apart? Why doesn't it drift like other weather systems? Some theorize Jupiter's magnetic field acts like an invisible cage, trapping the cold air in place. Others wonder if we're seeing evidence of a whole new type of atmospheric physics, where magnetic forces and weather intertwine in ways we've never witnessed. One thing's certain: Jupiter's skies hold far more secrets than we ever imagined, proving even familiar giants can surprise us. The moon's surface holds ghostly patterns that look like cosmic fingerprints, delicate, bright swirls stretching for miles across the dusty plains. Take Rheonir Gamma, one of the most striking examples, a swirling, labyrinthine formation nearly 50 miles wide, gleaming against the dark lunar mare like a half-erased chalk drawing. These aren't random quirks of erosion, they're magnetic anomalies with fields strong enough to deflect solar wind, creating bizarre mini-magnetospheres in a world that otherwise has no global magnetic field. How does a barren rock like the moon produce such intricate, localized magnetism? One theory points to comet impacts. When a comet slams into the surface at high speeds, its vaporized material could mix with molten debris, forming iron-rich compounds that retain magnetism as they cool. Imagine a cosmic painter flicking metallic ink across the moon, each droplet freezing into a magnetic swirl. But there's a problem. Some swirls, like Reiner Gamma, show no signs of an impact crater nearby. That's led scientists to another wild possibility: ancient volcanic activity. Billions of years ago, the moon's interior may have harbored pockets of molten iron. As lava erupted, it could have carried magnetic minerals to the surface, where they hardened in the sun's primordial magnetic field, a field far stronger than today's. Over time, these patches became fossilized records of the moon's fiery youth. Yet even this theory doesn't fully explain why the swirls are so sharply defined, or why their magnetism hasn't faded over eons. The real headache comes when these swirls clash with moon formation models. If the moon was born from a colossal impact between Earth and a Mars-sized body, as leading theories suggest, its tiny core should have cooled long ago, leaving no energy to sustain magnetic quirks. Yet here they are, defiant, gleaming puzzles on the lunar surface. Some researchers even speculate the swirls might be shielding pockets of ice in permanently shadowed craters nearby, turning them into accidental oases in a cosmic desert. Every Apollo rock and orbital scan adds pieces to the puzzle, but the moon's swirls keep their secrets locked in plain sight. While most planets lean slightly as they orbit the sun, Earth tilts at a cozy 23 degrees. Uranus performs a cosmic belly flop, rolling around the sun at a jaw-dropping 98-degree angle. Picture a spinning top knocked sideways, its north pole pointed almost directly at the sun during summer. This extreme tilt gives Uranus the strangest seasons in the solar system: 21-year winters plunged in endless night, followed by summers where the sun never sets. For a planet that should rotate like its neighbors, this drunken stagger demands explanation. The leading theory, a catastrophic collision. Simulations suggest a young Uranus might have been walloped by an Earth-sized protoplanet early in its history, knocking it sideways like a billiard ball struck off-center. The impact could have scrambled the planet's rotation while also explaining another quirk. Uranus' icy mantle appears oddly separated from its core, as if something violently stirred its interior. But here's where the mystery deepens. If such a violent impact occurred, where's the debris? Unlike Earth's moon, a clear souvenir of our own planetary smash-up, Uranus has no surviving remnants from this hypothetical crash. Even stranger, all 27 of its moons orbit neatly along its tilted equator, suggesting they formed after the event. Unless the impact was so precise it left no trace while perfectly reshaping the entire system, we're missing a critical piece of the puzzle. Meanwhile, Neptune-Uranus icy twin harbors its own thermodynamic riddle. Despite being farther from the sun than Uranus and receiving only 40% as much sunlight, Neptune radiates 2.6 times more heat than it absorbs. Its cloud tops blaze at -350 degrees Fahrenheit, yet its core simmers at a scorching 9,000 degrees hotter than the surface of the sun. This excess heat fuels the fastest winds in the solar system, howling at over 1,200 miles per hour. But where's this energy coming from? Voyager 2's flyby in 1989 revealed clues. Neptune's interior appears to churn with convection, as heavier helium droplets sink through hydrogen layers, releasing gravitational energy as heat, a process called Kelvin-Helmholtz contraction. Yet calculations suggest this mechanism alone can't account for Neptune's fiery output. Some speculate radioactive decay in its core or diamond rain, a phenomenon where carbon compresses into diamonds that sink, generating friction heat. But these theories remain unproven. The contrast between these ice giants couldn't be starker. Uranus, knocked sideways yet oddly cold, seems to have lost internal heat long ago. Neptune, perfectly upright but boiling inside, defies expectations of a world so distant from the sun. One thing's clear: the outer solar system plays by rules we're only beginning to decipher. Deep within the asteroid belt, dwarf planet Ceres harbors a sight unlike any other. a cluster of dazzling bright spots blazing from the floor of Oort crater like cosmic beacons. These radiant patches, some concentrated enough to outshine their surroundings by a factor of 5, first stunned astronomers when NASA, a Dawn spacecraft, arrived in 2015. Close-up images revealed the source salt deposits, primarily sodium carbonate, stretching across 6 miles of the crater's basin. But how did this briny spectacle form on a world just 590 miles wide? The answer divides scientists into two passionate camps, each with clues pointing to wildly different origins. One faction argues these deposits are the aftermath of cryovolcanism eruptions of salty water erupting from Ceres' subsurface ocean. Dawn's infrared spectrometer detected hydrated salts, suggesting liquid recently reached the surface before evaporating, leaving behind reflective residue like a celestial salt flat. Even more compelling, the crater's central dome, a 2,000-foot-high mound riddled with fractures, resembles terrestrial mud volcanoes where water and gases force their way upward. If brine is still oozing through these cracks, Ceres could be one of the solar system's rare active icy worlds, joining Enceladus and Europa in the ranks of potentially habitable bodies. But skeptics point to Oort's violent past. The crater itself, 57 miles across and 20 million years young, formed when a massive impactor punched through Ceres' crust. Could the collision have unearthed primordial salt deposits lurking beneath the surface? Impact simulations show the energy released might have melted underground ice, creating temporary briny lakes that later evaporated into the gleaming patches we see today. Adding fuel to this theory, similar bright spots appear in other Ceres craters, all relatively young, hinting at a system-wide reservoir of buried salts exposed only by recent strikes. The debate hinges on one critical question: are we seeing an ongoing process or frozen relics? Dawn's gravity data revealed a deep brine reservoir beneath Oort, but whether it's still percolating to the surface remains unresolved. Some researchers point to haze layers observed hovering above the crater at certain times, possibly water vapor escaping from below. Others counter that scattered sunlight or residual ice sublimation could explain the haze without invoking active geology. What makes Ceres' mystery so tantalizing is its accessibility. Unlike distant Europa or encased Enceladus, this dwarf planet's exposed surface offers a front-row seat to deciphering how small, icy worlds evolve. Those gleaming salts might be more than a scientific curiosity. They could be the fingerprints of a dynamic, water-rich past or even present, hiding in plain sight within our solar system's asteroid belt. Every unanswered question reminds us that sometimes the most profound discoveries come wrapped in the smallest packages. In the vast emptiness beyond Saturn, two robotic pioneers began slowing down in ways that defied the laws of physics. Pioneer 10 and 11, launched in the early 1970s to explore the outer solar system, should have coasted effortlessly through space. Yet by the time they passed Saturn's orbit, navigators noticed something bizarre. Both spacecraft were decelerating ever so slightly, as if an invisible hand were tugging them backward toward the sun. This tiny but persistent drift, just 300 billionths of a meter per second squared, became known as the Pioneer Anomaly, a cosmic hiccup that baffled scientists for decades. At first, researchers suspected mundane explanations, perhaps fuel leaks or instrument errors, but meticulous analysis ruled these out. The deceleration was too consistent, too uniform across both probes, separated by millions of miles. The anomaly pointed to something deeper, maybe even a flaw in our understanding of gravity itself. For years, physicists wrestled with radical possibilities. Was Einstein's theory of general relativity incomplete at these distances? Could there be unseen dark matter dragging on the probes? Or was some exotic new force at play in the outer solar system? Then came an elegant, if anticlimactic, solution: In 2012, a team calculated that heat radiating unevenly from the Pioneer's power systems could explain the drift. As their plutonium-powered generators decayed, warmth escaping from the backs of their dish-shaped antennas created a tiny recoil effect, like a car slowing when headlights shine photons backward. This thermal radiation matched the anomaly's magnitude perfectly. Case closed, or so it seemed, but space loves a plot twist. When New Horizons raced toward Pluto in 2015, scientists watched closely for any sign of the Pioneer effect. Yet the newer probe showed no anomalous slowdown. Why would thermal radiation affect the Pioneers but not New Horizons? The difference likely lies in their designs. New Horizons' power system radiates heat more symmetrically, cancelling out any directional push. But some researchers still wonder, did we explain too much away? The original thermal models required precise assumptions about how heat bounced inside the Pioneer's structures. Others argue the anomaly's resolution feels a bit too neat, like fitting a key to a lock after the fact. What remains is a cautionary tale about how even the tiniest discrepancies can reveal hidden layers of complexity. Whether a quirk of engineering or a whisper of deeper physics, the Pioneer anomaly reminds us that the universe often speaks in riddles, and the answers we find may only lead to richer questions. Beyond Neptune's orbit lies a cosmic boundary so abrupt it feels like nature drew a line in the sand, the Kuiper Cliff. Picture our solar system's icy outskirts as a bustling asteroid belt. Then suddenly, about 50 astronomical units from the Sun, the crowd of objects plummets to near zero. It's as if someone flipped a switch, halting the Kuiper belt sprawl with unnatural precision. This razor-sharp drop-off defies expectations. Standard planetary formation models predict a gradual thinning, not a hard stop. What could slice through the solar system's primordial debris field so cleanly? One tantalizing theory points to an unseen giant planet 9. This hypothetical world, estimated to be 5 to 10 times Earth's mass, might orbit hundreds of miles away, its gravity shepherding smaller objects into clustered orbits while clearing others like a cosmic snowplow. Computer simulations show such a planet could sculpt precisely the kind of sharp edge we observe. Yet even after years of searching, telescopes haven't spotted this phantom world, leaving astronomers divided. Could it be camouflaged by distance and darkness, or are we chasing a celestial mirage? Alternatively, the cliff might be a fossilized relic from the solar system's violent infancy. Early gravitational tugs from passing stars or the Milky Way's tidal forces could have stripped away outer objects, leaving this stark boundary. There's even a wilder possibility. What if our Sun was born in a dense star cluster, where neighboring stars' gravity snipped off the outer Kuiper belt like cosmic scissors? Each scenario leaves distinct fingerprints in the debris patterns, but the data remains frustratingly ambiguous. Now, New Horizons, the plucky probe that gave us our first close-up of Pluto, is racing toward this enigmatic frontier. Since its 2015 flyby, it's traveled over 20 miles deeper into the Kuiper belt, scanning for faint objects near the cliff's edge. Every icy body it spots helps reconstruct the solar system's hidden history. In 2019, it zipped past Arakoth, a primordial space snowman whose unchanged shape since formation offers clues about the Kuiper belt's early conditions. As the probe ventures farther, its instruments might detect subtle gravitational nudges, hints of unseen masses tugging at the fabric of space itself. The Kuiper Cliff isn't just a curiosity, it's a potential Rosetta Stone for decoding our solar system's past. Whether carved by a hidden planet, ancient stellar encounters, or forces we haven't imagined, this boundary challenges our understanding of how planetary systems evolve. And as New Horizons presses onward, each bite of data it beams back could tilt the scales between competing theories, or unveil something entirely unexpected at the edge of our cosmic neighborhood. Late one August night in 1977, an Ohio radio telescope captured a signal so extraordinary that an astronomer scrawled, "Wow, in red ink across its printout, a moment that would become legend in the hunt for extraterrestrial intelligence. The burst lasted 72 seconds, blaring from the constellation Sagittarius at precisely 1,420 MHz, the frequency of hydrogen, the universe's most abundant element and a logical interstellar hello if aliens were signaling across the cosmos. The signal's intensity spiked 30 times above background noise, matching all the hallmarks of an artificial transmission: narrow bandwidth, cosmic origin, and a strength suggesting a transmitter far beyond human capability. Yet the real mystery began when follow-up searches turned up nothing. Over decades, astronomers scoured the same patch of sky with increasingly sensitive instruments: the Very Large Array, the Allen Telescope Array, even the Hubble Space Telescope. Silence. The WOW signal became a cosmic one-hit wonder, leaving scientists grappling with two possibilities. Had we intercepted an alien beacon that switched off, or was there a natural explanation we'd missed? Enter the comet theory. In 2017, researchers proposed that two passing comets, 266P/Christensen and 335P/Gibbs, might have been the culprits. These icy wanderers, unknown in 1977, would have been releasing vast hydrogen clouds as solar heat vaporized their surfaces. As they drifted through the telescope's field of view, their expanding gas plumes could have mimicked an artificial signal. Skeptics quickly punched holes in the idea. The comets weren't precisely in the right location during the observation, and hydrogen clouds from such small bodies shouldn't produce a signal that intense. Alternative explanations range from pragmatic to profound. Maybe it was a reflected human signal, a military transmission or satellite echo bouncing off space debris, though none matched the frequency and direction. Others suggest an exotic astrophysical event, like a fortuitous alignment of a pulsar's beam or a random maser emission from a star-forming region. Then there's the haunting possibility that it truly was an alien transmission, perhaps a focused burst aimed elsewhere that we briefly intercepted as Earth moved through its beam, like a pedestrian catching a shred of a distant laser light show. What makes the WOW signal endure isn't just its unresolved nature, but what it reveals about our search for cosmic company. It remains the gold standard for potential ET detections. A reminder that the universe can produce phenomena indistinguishable from intelligence. Future telescopes like the Square Kilometre Array may finally solve the riddle, scanning millions of frequencies simultaneously with enough sensitivity to spot even fleeting cosmic whispers. Until then, that red-inked WOW stands as both a triumph and a taunt, proof that the cosmos knows how to keep its most thrilling secrets. For decades, whispers have swirled about an otherworldly sentinel silently circling Earth, the so-called Black Knight satellite. Stories claim this enigmatic object, allegedly thousands of years old, broadcasts mysterious signals while defying all known human technology. Some even suggest it's an alien probe sent to observe us, its origins lost to prehistoric antiquity. But peel back the layers of this cosmic legend, and you'll find a far more terrestrial and fascinating truth tangled in the chaos of the early space age. The myth's modern incarnation began in 1960, when newspapers reported an unidentified dark object in polar orbit, a feat beyond both American and Soviet capabilities at the time. Conspiracy theorists latched onto the story, stitching together disparate events into a grand narrative. A decade earlier, inventor Nikola Tesla had picked up odd radio repeats he believed were extraterrestrial in origin. Then in 1927, Norwegian engineers detected long-delay echoes radio signals bouncing back seconds after transmission, as if something in space was reflecting them. These fragments, skeptics argue, were misinterpreted natural phenomena, meteors ionizing the atmosphere or auroral disturbances, but woven together, they birthed the Black Knight legend. The satellite's proof came in 1998, when grainy photos from a space shuttle mission showed a jagged, asymmetrical shape floating against Earth's curvature. UFO enthusiasts declared it the Black Night, but engineers quickly recognized something mundane, a lost thermal blanket. These multi-layered insulation sheets, critical for shielding astronauts from extreme temperatures, occasionally drift free during spacewalks. Their crumpled, reflective surfaces catch sunlight in eerie ways, creating the illusion of structured craft when photographed from certain angles. Yet the most ironic twist lies in the Black Knight's supposed orbit. Early reports placed it in a polar trajectory precisely where America's first reconnaissance satellites, the Covert Corona program, operated in the 1960s. Classified missions like these often left debris in unusual orbits, fueling confusion among civilian observers. Even today, tens of thousands of human-made objects encircle Earth, discarded rocket stages, dead satellites, and fragments from collisions, creating a celestial junkyard ripe for misinterpretation. What makes this myth endure isn't just our love of mystery, but a deeper truth about how we navigate the unknown. Every unexplained echo or glint in space becomes a mirror reflecting our hopes and fears about what might be watching from the void. The real Black Knight isn't some ancient alien artifact. It's the human imagination itself, forever weaving stories among the stars. Mercury might be the solar system's smallest planet, but it packs two of its most baffling geological oddities, features so strange they've forced scientists to rethink how rocky worlds evolve. First, there are the hollows, thousands of bright, irregular depressions scattered across Mercury's surface like cosmic glitter. Some span miles, while others are no larger than a house, all with sharply defined edges and interiors so reflective they outshine everything around them. These aren't impact craters or lava tubes, they look like the planet is slowly dissolving from within. The leading theory suggests Mercury's hollows are the result of volatile materials, metals like sodium or sulfur sublimating directly from solid to gas when exposed to the harsh conditions near the sun. Imagine a block of dry ice shrinking away in sunlight, but on a planetary scale. Sunlight here is 11 times more intense than on Earth, and surface temperatures swing between 800 degrees Fahrenheit during the day and -290 at night. This extreme environment could be literally baking metals out of Mercury's crust, leaving behind these bizarre sunken pits. Some hollows even appear to be actively growing, with fresh, bright material exposed along their edges, evidence that this process isn't just ancient history but an ongoing planetary spectacle. Yet Mercury's second mystery might be even more profound, its absurdly oversized core. For a planet just slightly larger than Earth's moon, Mercury's core makes up a staggering 60% of its volume, twice the proportion of Earth. How did such a small world end up with so much metal crammed inside? The most dramatic explanation points to a cataclysmic collision early in Mercury's history. A protoplanet the size of Mars might have slammed into it, blasting away much of its rocky mantle and leaving behind a dense, metal-rich remnant. Computer simulations show such an impact could strip a planet down to its core while still allowing it to reaccumulate a thin crust over time. But not all researchers are convinced. Alternative theories suggest Mercury might have formed from unusually iron-rich building blocks in the inner solar system, or that the sun's intense heat vaporized part of its outer layers, leaving the core exposed. Every model has holes, literally. If a giant impact occurred, where's the debris, and why don't other inner planets show similar scarring? That's where BP Colombo comes in. This joint ESA-JAXA mission, currently orbiting Mercury, is armed with instruments designed to unravel these puzzles. Spectrometers are mapping the hollow's composition in unprecedented detail, hunting for those elusive volatiles. Meanwhile, precise gravity measurements will probe the core's structure. Is it partially molten? And does it hold clues to Mercury's violent infancy? Every new data stream brings us closer to understanding how this tiny, metal-packed world defies expectations. Together, these mysteries paint Mercury not as a static relic, but as a dynamic laboratory for extreme planetary processes. Whether sculpted by slow-motion evaporation or a primordial catastrophe, its surface and interior challenge our assumptions about how planets form and what secrets might lurk on scorched worlds orbiting distant stars. Far beyond Neptune's realm, where sunlight fades to a dim memory, the solar system's final frontier should be teeming with icy debris, the Oort cloud. Theorized as a vast spherical shell of frozen leftovers from our planetary beginnings, this distant reservoir is thought to stretch halfway to the nearest star. Yet decades of searching have left astronomers with a glaring puzzle. Whereas all the mass, the Oort cloud's existence hinges on a cosmic breadcrumb trail, long-period comets. These icy wanderers, some taking millions of years to complete a single orbit, swing in from random directions, suggesting a spherical source rather than the flat Kuiper belt. But here's the catch. To fling comets our way so consistently, the Oort cloud should weigh between 5 and 20 times Earth's mass. Current surveys, however, have detected less than 1% of that. Even our most powerful telescopes struggle to spot these primordial snowballs so far out they're too faint, too spread out, and radiating almost no heat. This discrepancy opens a Pandora's box of possibilities. Could the Oort cloud's mass hide in stealthy, planet-sized objects? Some propose rogue planets ejected during the solar system's chaotic youth might lurk there, their gravity stirring the comet population. Others speculate we're seeing echoes of the Sun's birth cluster comets stolen from sibling stars when they drifted apart 4 billion years ago. Then there's the wild card, dark matter. While most dark matter models place it galaxy-wide, not clustered around stars, a tiny fraction could theoretically get trapped by the Sun's gravity, masquerading as missing Oort cloud mass. The Vera Rubin Observatory, set to scan the skies later this decade, might finally tip the scales. Its ultra-sensitive cameras could spot larger Oort cloud objects previously invisible to us. Every undiscovered body peels back another layer of this frozen enigma, revealing whether our solar system's outer halo is a ghostly remnant or something far stranger. What makes this hunt so compelling isn't just the missing ice. The Oort cloud is a fossil record of our cosmic neighborhood's earliest days. Its structure, or lack thereof, could reveal ancient stellar encounters, the Sun's long-lost siblings, even clues about how other star systems organize their debris. Until we peer deeper into that frigid abyss, the question remains, is the Oort cloud a sparsely filled attic or a treasure trove hiding in the shadows? Pluto's frozen heart isn't just a charming geological quirk. It's a dynamic engine driving the dwarf planet's alien weather. Sputnik Planitia, that sprawling, heart-shaped basin of nitrogen ice, behaves less like a static feature and more like a cosmic lava lamp, endlessly churning and reshaping Pluto's surface in ways scientists never anticipated. When New Horizons swooped past in 2015, it revealed a glacier nearly 600 miles wide, split into polygonal cells that slowly convect, carrying fresh ice upward while older material sinks. This isn't just ice sliding around, it's a full-blown atmospheric puppet master. Here's the twist: nitrogen's peculiar properties at Pluto's frigid -390 degrees Fahrenheit turn Sputnik into a climate control system. During the dwarf planet's long afternoon, sunlight vaporizes nitrogen from the glacier's western edge, creating a thin but measurable atmosphere. As Pluto rotates, these gases freeze back onto the eastern lobe, completing a cycle that powers winds blowing opposite to the planet's spin. Imagine a celestial air conditioner where frost doesn't just form, it migrates across the surface in a planet-wide heartbeat, sculpting dunes of methane ice and erasing impact craters as it goes. The real head-scratcher is how this tiny world, with just 1/600th of Earth's atmospheric pressure, sustains such complexity. Traditional climate models assumed dwarf planets were inert snowballs, but Sputnik Planitia laughs in the face of those assumptions. Its convection cells, some spanning 20 miles across, operate on timescales of 500,000 years slow by human standards, but positively hyperactive for a body this small and cold. Even more baffling, the glacier's location smack on Pluto's equator, aligned almost perfectly opposite its largest moon, Charon. Some scientists think gravitational tides from this orbital dance might have helped trap the ice there, creating a self-reinforcing cycle where the basin grows ever deeper as more nitrogen accumulates. Yet the mysteries multiply. New Horizons spotted pits on Sputnik's surface that appear to be actively growing, possibly from sublimation, while neighboring regions gleam with fresh deposits. And then there's the bladed terrain just east of the heart of jagged, skyscraper-tall ridges of methane ice that might be fossilized remnants of ancient climate cycles. Each feature suggests Pluto's heart doesn't just beat. It sings in multiple geological registers, a symphony of ice and gas that rewrites the textbooks on how small, cold worlds evolve. What makes Sputnik Planitia truly revolutionary is its implication for other distant bodies. If a dwarf planet with barely any atmosphere can host such active processes, what might lurk on similar worlds in the Kuiper belt? The answer could reshape our search for dynamic environments, and maybe even habitable niches in the solar system's frozen outskirts. For now, Pluto's heart keeps its secrets pulsing quietly in the dark, a reminder that even the smallest worlds can harbor grand surprises. The universe is supposed to expand in all directions equally, a grand, uniform stretching of space itself. But in 2008, astronomers analyzing data from hundreds of galaxy clusters stumbled upon something that shouldn't exist. A mysterious cosmic current carrying entire superclusters toward one specific corner of the sky. They called it the dark flow, and it's as if someone left a celestial faucet running, pulling galaxies toward an unseen drain beyond the edge of our observable universe. The initial findings came from NAS, a Wilkinson microwave anisotropy probe which studied the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light should be random, but researchers noticed a peculiar pattern. Galaxy clusters racing at nearly 2 million miles per hour showed a slight Doppler shift, their collective motion imprinted like a fingerprint on the CMB. This wasn't just local movement, it spanned billions of light years, a coordinated march toward the constellations Centaurus and Hydra that defied conventional models of cosmic expansion. Skeptics argued it could be systematic error, perhaps dust interference or calibration quirks, but subsequent studies using X-ray telescopes to track over 1,000 clusters confirmed the anomaly. Even stranger, the flow's reach extended farther than it should. Gravitational attraction from known structures like the Shapley supercluster can tug on nearby galaxies, but the dark flow's scope suggests something far more massive lurking in the cosmic shadows. That's where theories get radical. One possibility, a supermassive structure beyond our cosmic horizon, a rebel patch of space-time that broke away during inflation, carrying its own gravitational influence. Another mind-bending idea, our universe might be brushing against a neighboring bubble of space-time in the multiverse, its gravity leaking through like magnetism through a wall. If true, the dark flow could be our first indirect evidence of realms existing outside our observable cosmos. Yet the mystery deepens with every new observation. The European Space Agency's Planck satellite, designed to measure CMB with unprecedented precision, failed to confirm the effect at first glance, only for reanalysis to suggest the signal might still lurk in the noise. Meanwhile, some theorists propose the flow isn't motion at all, but a remnant of primordial gravitational waves distorting our measurements. What makes the dark flow so thrilling isn't just its defiance of cosmology textbooks, it's the audacity of its implications. Either we're standing at the shoreline of an uncharted cosmic ocean, sensing tides from invisible continents, or our understanding of gravity has fundamental gaps. As next-generation telescopes like the Nancy Grace Roman Space Telescope come online, they'll scan deeper into this enigmatic current, searching for ripples that might finally reveal what, or what's beyond, is pulling the strings. In the summer of 1976, NASA Viking 1 orbiter captured an image that would ignite decades of speculation. A mile-long mesa in the Cydonia region of Mars, eerily resembling a human face staring blankly into space. The grainy black and white photo showed what appeared to be symmetrical eyes, a nose, and even a faint mouth carved into the rock. News headlines ran wild with theories. Was this an ancient alien monument, a sign of lost Martian civilization, or just a trick of light and shadow? Fast forward to the 21st century, and high-resolution cameras like HiRISE aboard the Mars Reconnaissance Orbiter have scrutinized the so-called face on Mars with stunning clarity. The new images reveal something far less sensational: an ordinary mesa heavily eroded by wind and time, its features reduced to rugged cliffs and chaotic debris fields. The symmetry that once suggested artistry now appears as nothing more than a fortuitous alignment of ridges and shadows in that single Viking snapshot. Scientists call this psychological phenomenon pareidolia, the human brain's tendency to impose familiar patterns like faces on random shapes. It's why we see elephants in clouds or the man in the moon. Yet the face on Mars endures as a cultural touchstone, revealing more about us than the red planet. Conspiracy theories flourished precisely because space exploration feels deeply personal. We project our hopes, fears, and myths onto cosmic blank canvases. The face became a Rorschach test for our fascination with extraterrestrial life, amplified by pop culture. Films like Mission to Mars and TV shows spun elaborate tales around it, while skeptics and believers clashed in endless debates. What makes this myth so resilient isn't just pareidolia, but how it mirrors humanity's hunger for connection in a vast, seemingly empty universe. When Viking first glimpsed that mesa, Mars was still a mystery, a world of imagined canals and alien invasions. Today, as rovers tread its dusty plains, we know the planet as a real place with wind-sculpted rocks and dry riverbeds. But the face's legacy lingers as a cautionary tale about interpreting the unknown. The next time you spot a smiling crater or a dragon-shaped ridge in planetary photos, remember, the cosmos is full of wonders that need no embellishment. Mars' real mysteries, its vanished water, hidden aquifers, or potential microbial fossils, are compelling enough without phantom faces. Yet that weathered mesa in Cydonia still whispers a timeless truth. When we gaze into the abyss, we often find our own reflections staring back. Saturn's moon Titan looks like Earth in a funhouse mirror, a world with weather, rivers, and vast liquid basins, but where the chemistry reads like science fiction. Here, temperatures hover around -290 degrees Fahrenheit, turning water into rock-hard ice and methane into the dominant liquid, the result. A landscape where liquid methane rains from orange-hazed skies, carves valleys into water-ice bedrock, and gathers in sprawling lakes near the poles. When the Cassini probe mapped Titan's surface, it revealed shorelines eerily reminiscent of Earth's Great Lakes, complete with river deltas and evaporite deposits, except these water features are filled with liquefied natural gas. The scale of Titan's methane cycle is staggering. Kraken Mare, the largest lake, sprawls over 150,000 square miles, bigger than Earth's Caspian Sea. Radar images show waves rippling its surface, stirred by winds in the moon's dense nitrogen atmosphere. Even more mind-bending, seasonal changes. During Titan's 30 Earth-year seasons, methane clouds drift and burst, filling lake basins in the winter, then evaporating in summer, leaving behind pancake-flat ghost lakes of dried hydrocarbons. It's a water cycle turned inside out, proving that nature can reinvent familiar processes in the strangest environments. Yet Titan's methane mystery goes deeper than weather. Where does all this liquid come from? Unlike Earth's self-replenishing oceans, Titan's surface methane should have been broken apart by sunlight over millions of years. Some hidden reservoir, perhaps a vast underground methane aquifer, must be seeping upward to keep the lakes filled. The upcoming Dragonfly mission, a nuclear-powered drone set to launch in 2027, will hunt for these answers, skimming Titan's dunes and sampling its organics to decode how this alien hydrologic engine runs. Meanwhile, just 800,000 miles away, Saturn's tiny moon Enceladus stages an even more tantalizing show. At just 310 miles wide, small enough to fit inside Arizona, this icy speck shouldn't be geologically active. Yet Cassini spotted massive plumes gushing from its south pole, shooting water ice and organic compounds into space at 800 miles per hour. These aren't just surface eruptions, they're taps into a global subsurface ocean, one kept liquid by gravitational flexing from Saturn's tides. The numbers stunned scientists. Enceladus Ocean may be twice as deep as Earth's, capped by an ice shell averaging 12 miles thick. Hydrothermal vents on its seafloor, much like those fueling life at Earth's ocean trenches, could be dissolving minerals into the water. Cassini's dust analyzer even detected silica nanoparticles, a telltale sign of hot rock-water interactions. More startling, the plumes contain hydrogen, methane, and complex carbon chains, the chemical building blocks microbes thrive on. What makes these moons a perfect pair of cosmic puzzles is how they represent opposite extremes in the search for alien environments. Titan's methane lakes offer a window into how chemistry might work without water, while Enceladus' salty jets scream habitable by earthly standards. One shows us how alien life could arise in unexpected solvents. The other dangles the prospect of life as we know it, thriving in the dark beneath an icy crust. Together, they prove that even in our solar system, nature's playbook has more chapters than we ever imagined. Look up at the western sky just after sunset or before dawn, and you might spot an eerie, faint pyramid of light stretching from the horizon, a phenomenon called the zodiacal light. This ethereal glow, sometimes mistaken for distant city lights or even the Milky Way, comes from billions of dust particles orbiting the sun, reflecting sunlight like a cosmic mirror. But where does all this interplanetary dust come from? The answer has sparked a heated debate among astronomers, with two leading suspects: comets leaving icy debris in their wakes, or asteroids grinding each other down in violent collisions. For decades, conventional wisdom pointed to asteroids as the primary source. The logic seemed sound: rocky bodies smashing together in the asteroid belt would naturally produce clouds of fine particles. But when NASA LADEE mission Lunar Atmosphere and Dust Environment Explorer studied dust around the moon in 2013, it threw a wrench into that theory. The probe detected unexpected spikes in dust density, with particle compositions matching the fluffy, porous texture of comet material rather than the denser fragments expected from asteroid collisions. Even more puzzling, these dust clouds appeared to vary with meteor showers events tied to comet trails, not asteroids. The plot thickened when scientists realized the zodiacal dust doesn't behave like typical asteroid debris. Instead of being evenly distributed, it clusters in bands and spirals, following orbits suspiciously similar to known comets like Encke and Halley. Some researchers argue this points to comets as the dominant suppliers, shedding dust as their icy nuclei vaporize near the sun. Others counter that asteroid collisions could still contribute, especially from families like the Charon cluster, known to produce fresh debris through ongoing crashes. Then there's the wild card: interstellar dust. Recent studies suggest a fraction of the zodiacal particles might not even originate in our solar system. The Parker Solar Probe detected ultra-fine grains that could be interstellar hitchhikers, swept into our cosmic neighborhood by the solar wind. If confirmed, this would mean the zodiacal light isn't just a reflection of our solar system's history, but a glimpse into the broader galaxy's dust cycle. What makes this mystery so compelling isn't just the scientific tug of war, it's the sheer scale of the puzzle. The zodiacal dust cloud spans the entire inner solar system, from Mercury to Jupiter, containing enough material to build a mountain range. Yet it's so diffuse that if you gathered all of it, it would fit inside a single stadium. This delicate balance between abundance and invisibility is what keeps astronomers searching for answers. The next time you spot that ghostly pyramid of light, remember, you're not just seeing dust, you're witnessing a cosmic crime scene where comets, asteroids, and maybe even interstellar travelers leave their fingerprints across the sky. And with every new mission, from LADEE to future probes like the planned Interstellar Mapping and Acceleration Probe, we get closer to solving the riddle of where this celestial glitter truly comes from. The Moon's gravity field isn't the smooth, predictable pull we once imagined. It's more like a cosmic obstacle course with invisible speed bumps that nearly sent early space missions careening off course. These hidden anomalies, called mass concentrations or mascons, are dense regions lurking beneath the lunar surface that tug on orbiting spacecraft with unexpected force. When Apollo astronauts circled the Moon in the late 1960s, mission controllers noticed their orbits wobbling unpredictably. Without warning, the lunar module would suddenly gain or lose altitude, as if some unseen hand were nudging it off its path. The culprit, ancient lava seas that hardened billions of years ago, their iron-rich remains buried just beneath the dusty regolith like planetary anchors warping space-time itself. Mascons reveal the Moon's violent past in ways craters alone cannot. Picture the solar system's early days when massive asteroids punched through the lunar crust, creating giant basins like Imbrium and Serenitatis. Molten rock from the Moon's interior welled up to fill these wounds, then cooled into dense basaltic plains we now call mare. But unlike Earth's shifting tectonic plates, the Moon's rigid crust locked these heavy deposits in place forever, creating permanent gravitational hotspots. Today, spacecraft passing just 60 miles above these regions can experience orbital altitude shifts of hundreds of feet, enough to doom an unprepared mission. The Apollo program learned this lesson the hard way. During the historic Apollo 11 landing, Eagle's orbit began decaying unexpectedly, forcing Neil Armstrong and Buzz Aldrin to burn precious fuel to compensate. Later analysis showed they'd flown directly over Mare Tranquillitatis' mascon, its extra gravity dragging them moonward like quicksand. NASA engineers scrambled to adjust subsequent missions, tweaking orbits to skirt these invisible traps. Modern lunar orbiters like Grail Gravity Recovery and Interior Laboratory have mapped these gravitational potholes in exquisite detail, revealing mascons as bullseye patterns, a dense central zone surrounded by a ring of strangely low gravity. This bizarre target pattern likely formed as the heavy lava pooled, flexing the crust downward while leaving lighter peripheral material uplifted at the edges. The Moon's lack of erosion preserves these billion-year-old fingerprints perfectly, offering scientists a window into early solar system bombardment. What makes mascons more than just historical curiosities is their ongoing threat to lunar exploration. As nations race to establish moon bases, precise orbital calculations will be crucial, especially for proposed frozen orbit trajectories designed to minimize fuel use. Future lunar GPS systems may need real-time mascon adjustments, much like pilots account for wind shear. These gravitational quirks remind us that even our closest celestial neighbor still guards surprises, its hidden heaviness waiting to test our next giant leap. The Sun's corona burns with a heat that defies logic, a blazing halo stretching millions of miles into space, where temperatures soar to over 1,000,000 degrees Celsius. Meanwhile, the solar surface below simmers at a comparatively cool 5,500 degrees. It's like standing next to a campfire and feeling the air around you grow hotter than the flames themselves. This cosmic contradiction, known as the coronal heating problem, has puzzled scientists for nearly a century. How can the Sun's atmosphere be hundreds of times hotter than its surface? Recent breakthroughs from NASA Parker Solar Probe, the first spacecraft to touch the Sun, are rewriting the rulebook, flying within 4 million miles of the solar surface, closer than any mission before it. Parker discovered a hidden universe of magnetic turmoil. Its instruments captured evidence of countless tiny energy bursts dubbed campfires, miniature solar flares no larger than a city, peppering the corona like sparks from a bonfire. These fleeting eruptions, each lasting mere seconds, may collectively pump enough heat into the corona to explain its scorching temperatures. But the plot thickens with nanoflares, even smaller explosions theorized to occur at scales too tiny for current telescopes to spot. Imagine billions of microscopic firecrackers detonating every second across the Sun's atmosphere, their combined energy dwarfing the occasional massive flares we see from Earth. Parker's data hints that these nanoflares could be the corona's secret furnace, converting tangled magnetic fields into heat through a process called magnetic reconnection. When opposing magnetic field lines snap and realign, they release colossal energy like rubber bands breaking and whipping outward, yet mysteries linger. Why does reconnection happen so efficiently in the corona? Why doesn't this energy dissipate before heating the plasma? Some theories suggest turbulent plasma waves act as intermediaries, channeling energy from magnetic fields into particles. Others propose that the corona's extreme thinness, a vacuum by Earth standards, allows electrons to race freely, carrying heat without colliding enough to cool down. Every Parker flyby peels back another layer of this enigma. The probe's latest orbits reveal switchback-shaped kinks in the solar wind's magnetic field, possible remnants of nanoflare activity. Meanwhile, ground-based telescopes like DKIST, the world's most powerful solar observatory, zoom in on magnetic braids unraveling in real time. Together, they're painting a portrait of a corona alive with invisible energy, crackling with forces we're only beginning to measure. Solving this puzzle isn't just academic, it's vital for predicting solar storms that threaten satellites and power grids. If nanoflares indeed drive coronal heating, their patterns could offer early warnings for disruptive space weather. The Sun's fiery halo, once a paradox, now stands as a testament to nature's ability to hide its most profound truths in plain sight, if only we dare get close enough to look. Saturn's iconic hexagon isn't just a flat, two-dimensional pattern. It's a towering skyscraper of swirling gas, plunging nearly 200 miles deep into the planet's atmosphere. New three-dimensional simulations reveal this six-sided storm isn't confined to the cloud tops where we see it. It's more like a colossal rotating column, a planetary-scale vortex with roots anchored deep in Saturn's churning interior. Imagine a hurricane so vast it could stretch from Earth's surface to the edge of space, its walls sculpted by forces we're only beginning to understand. Scientists first pieced together the hexagon's vertical structure using data from NASA's Cassini mission, which spent 13 years studying Saturn. By analyzing temperature variations and wind speeds at different altitudes, researchers realized the hexagon isn't just a surface feature. It's a stacked system of winds, with each layer influencing the next. The upper clouds whip around at 300 miles per hour, while deeper layers rotate more slowly, creating a shear that somehow stabilizes the geometric shape instead of tearing it apart. It's as if the entire structure is synchronized, like a cosmic ballet where every dancer moves in perfect harmony to maintain the formation. Here on Earth, researchers are recreating Saturn's hexagon in labs using spinning tanks of fluid, a cosmic chemistry set to decode its secrets. In one experiment at Oxford University, scientists filled a circular container with water, placed a small ring at its center, and set the whole apparatus rotating. When the inner ring spun faster than the outer tank, something remarkable happened. The fluid spontaneously organized into polygons, including a near-perfect hexagon. The key ingredient: shear the difference in speed between adjacent layers of fluid. This mimics what's happening on Saturn, where atmospheric layers slide past one another at varying velocities, creating stability through chaos. But lab experiments only tell part of the story. Saturn's hexagon endures for decades, possibly centuries, while laboratory polygons flicker in and out of existence. The missing piece might be the planet's own rotation. Saturn spins so fast, completing a day in just 10.5 hours, that its Coriolis force, the same effect that twists hurricanes on Earth, could be acting like an invisible mold, shaping the turbulence into that unmistakable six-sided form. Add to this the planet's lack of a solid surface, allowing storms to rage unimpeded for generations, and you have a recipe for a meteorological marvel. Yet the deepest mystery isn't just how the hexagon forms, but why it's so stubbornly stable. Most atmospheric features dissipate as energy radiates outward, but Saturn's hexagon behaves like a self-repairing machine. Some theories suggest standing waves oscillations that reinforce rather than cancel each other might be trapping energy within the structure. Others propose the hexagon is a Rossby wave, a planetary-scale ripple that channels energy back into itself like a feedback loop. Whatever the mechanism, this storm is a masterclass in efficiency, a natural engine that converts chaos into order on a mind-bending scale. What makes these discoveries so thrilling is their universality. The same physics governing Saturn's hexagon might apply to other gas giants, or even to the swirling disks of young solar systems where planets are born. By cracking this code, we're not just solving a puzzle on Saturn, we're peering into the fundamental laws that shape spinning systems across the cosmos. And as future missions probe deeper into the atmospheres of exoplanets, the lessons learned from this six-sided enigma could help us recognize other geometric wonders hiding in the skies of distant worlds. For now, Saturn's hexagon remains a testament to nature's ability to carve precision from pandemonium. It's a reminder that even in the chaos of a gas giant's skies, there's an underlying order, one that's waiting for us to decipher its rules. And with every lab experiment and computer model, we're inching closer to understanding how a storm can become a work of art. The wow signal's resurgence in scientific debate comes with a surprising twist. Fresh analysis has dismantled one of the most popular natural explanations. Back in 2017, researchers proposed that two previously undiscovered comets, 266P Christensen and 335P Gibbs, might have been responsible for the infamous burst. These icy bodies, unknown in 1977 when the signal was detected, were thought to release vast clouds of hydrogen as they neared the Sun, potentially mimicking an artificial transmission. But 2023 spectroscopic studies delivered a devastating blow to this theory. Here's why the comet explanation collapsed. The wow signal's frequency was locked precisely at 1,420 MHz, the electromagnetic signature of neutral hydrogen, the most common element in the universe. While comets do release hydrogen, their emissions are messy and broadband, smeared across a range of frequencies. The wow signal, by contrast, was razor-sharp, occupying a bandwidth of less than 10 kHz, narrower than even human-made radio stations. Modern simulations show comet-produced hydrogen simply couldn't achieve such a focused, intense spike. It'd be like expecting static from a broken radio to suddenly play a perfect symphony. Even more damning, the comet's orbits. Detailed reconstructions placed them too far from the wow signal's observed coordinates in Sagittarius during the critical 72-second window. Their hydrogen clouds would have been diffuse and faint by the time they drifted into the telescope's field of view. This leaves astronomers with a thornier question: if not comets, then what? The signal's precision still rules out most known astrophysical phenomena. Pulsars, for instance, produce regular pulses, not one-off bursts. Cosmic masers, natural microwave lasers, emit broader frequencies. Even atmospheric reflections of human signals fail to match both the frequency and the signal's rapid intensity curve. This vacuum of conventional explanations has reignited discussions about artificial origins. The signal's bandwidth aligns eerily well with what theorists predict an intentional interstellar beacon might use, narrow enough to stand out from cosmic noise, yet broad enough to carry meaningful information. Its intensity suggests a transmitter far more powerful than anything humans built in the 1970s, possibly harnessing the energy of a star for amplification. And then there's the chilling coincidence of its frequency. Hydrogen's emission line is often called the universal watering hole, a logical channel for civilizations to announce their presence. Yet mysteries linger. If the WOW signal was a deliberate transmission, why hasn't it repeated? SETI Allen Telescope Array has monitored the region for over 1,000 hours with no recurrence. Some speculate the original burst might have been a fleeting, one-time sweep like a lighthouse beam momentarily flashing in our direction. Others wonder if we caught a fragment of a longer message, its full structure lost in the cosmic static. The debate now hinges on next-generation instruments. The upcoming square-kilometer array, with its unprecedented sensitivity, could detect similar signals from thousands of light-years away, testing whether the WOW anomaly was a fluke or a signpost in a much larger conversation. Until then, that red-inked exclamation on a decades-old printout remains both a tantalizing clue and a humbling reminder the universe might be shouting, but we're still learning how to listen. The Oort cloud's most baffling feature isn't what's there, it's what isn't. Theory suggests this icy halo should weigh between 5 and 20 Earth masses, yet observations detect barely 1% of that. So where's the missing material? One provocative answer lies in the interstellar trespassers breezing through our solar system. Objects like Oumuamua, the cryptic cigar-shaped visitor spotted in 2017. Simulations now suggest these cosmic nomads might be raiding our Oort cloud, yanking comets away like invisible thieves in the night. Picture the Oort cloud as a loosely bound snow globe of comets, barely tethered to the sun's gravity. When an object like Oumuamua zips through at high speed, its gravitational pull could fling hundreds of comets into the void. Recent models from the University of Bordeaux show a single interstellar passerby could strip away several Earth masses of material over billions of years. And here's the kicker: Oumuamua isn't alone. Astronomers estimate thousands of such objects drift through the solar system undetected, each potentially leaving with a gravitational souvenir. But the plot thickens when you consider timing. The Oort cloud formed during the solar system's infancy, when the Sun was still nestled in its birth cluster alongside sibling stars. Back then, close encounters with neighboring stars and rogue planets would have been frequent, far more disruptive than today's relative calm. Some researchers argue this early chaos could explain the bulk of the missing mass. Imagine a cosmic game of pinball where passing stars plucked comets from our outer reaches while their own Oort clouds lost material to us. Over eons, this gravitational exchange would leave all star systems with depleted debris fields. Yet alternative theories persist. Could dark matter be masquerading as missing Oort mass? While most dark matter models distribute it galaxy-wide, a fraction might linger near stars, subtly altering comet orbits. Others propose the Oort cloud was never as massive as we thought, that comets form more efficiently in collapsing molecular clouds, leaving less leftover material to begin with. The Vera Rubin Observatory's upcoming sky surveys may tip the scales. By spotting more interloper objects like Oumuamua and tracking their paths, we could finally measure how much material they steal. Every unaccounted-for comet is a clue, a breadcrumb leading us closer to understanding whether our solar system's outer fringe is a plundered relic or simply lighter than we imagined. Until then, the Oort cloud's vanishing act remains one of astronomy's greatest sleight-of-hand mysteries. From Jupiter's churning Great Red Spot to Saturn's impossible hexagon, from the phantom pull of the Pioneer anomaly to the haunting silence of the WOW signal, these 25 cosmic puzzles aren't just unsolved mysteries. They're the solar system's greatest cold cases, each one a tantalizing clue waiting to crack open our understanding of the universe. Think of them as celestial breadcrumbs scattered across planets, moons, and the void between, leading us toward revelations we can't yet imagine. Every bizarre geological formation, every unexplained atmospheric quirk, every gravitational hiccup is a challenge thrown down by nature itself, daring us to look deeper, think harder, and question everything we thought we knew. Take the way Pluto's frozen heart reshapes its own world, or how Mercury's hollows seem to dissolve before our eyes. These aren't static oddities, they're active laboratories, proving that even in the farthest reaches of our solar system, the story isn't over. It's still being written, and with every mission we launch, every telescope we point skyward, we're not just chasing answers, we're rewriting the textbooks. The Kuiper Cliff's sharp edge, the Oort cloud's vanishing mass, the dark flow's cosmic tug-of-war, they're not roadblocks, they're signposts pointing toward gaps in our knowledge where the next breakthroughs lie. That's the beautiful paradox of science. The more we uncover, the more questions we find. And that's where you come in. Which of these 25 phenomena keeps you up at night? Is it the methane whispers of Mars hinting at life we can't yet prove? The hexagonal storm on Saturn defying physics with every rotation? Or maybe it's the Tunguska event, a cosmic whodunit with no crater to blame? Drop your pick in the comments. Let's crowdsource the solar system's next great detective story. And if you're hungry for more cosmic conundrums, don't forget to hit subscribe. Part 2 is already brewing, packed with even deeper dives into the universe's most head-scratching secrets, because the solar system isn't done surprising us, and neither are we. The next big discovery could be lurking in data we've already collected or waiting for that one bold mission we've yet to launch. So stay curious, stay skeptical, and above all, keep looking up. The universe has plenty more puzzles up its sleeve.